Thank you very much. So, welcome everyone. Good for my ego to have a big audience, but that's probably just because there's no other presentation at the same time in the other room. So I guess everybody knows me. My name is Böhme. I work for SerNet. I work on Samba since more than 10 years by now. And some time ago, I got the pleasure of starting some work on directory leases. That was in 2020, roughly, I think, where we had a customer asking us, hey, what about directory leases? And then we kind of went, oh, how hard can it be? Let's do a proof of concept. And I think we had something with not too much effort that worked to some extent, but it was very clear that a lot more effort would be needed. So, and now fast forward 5 years, 2025, this year, or no, actually last year. So in 2024, at the end of 2024, in October or November, I think, I was able finally, after so much time, to continue to work on this proof of concept that I still had in some branch sitting on my laptop or on git.samba.org as part of the STF funding, which you may remember Mirko Swillos talked about yesterday. So this was really, really awesome to be able to pick this up and continue working on that. And so in this presentation, I want to give a quick introduction about what are actually leases, because directory leases are very related to leases. Then tell a few interesting stories about issues that I ran into when picking up the work again on the directory leases and implementing them. See if I can highlight a few real-world benefits of actually having a server, Samba server, with directory leases enabled and the client connecting to the server, and then seeing, okay, is it actually any better now that we've implemented it? And then some Q&A at the end. And of course, as in all other presentations, I guess, if you have questions in between, just raise your hand. Maybe wait for Alina to get with the microphone to you, so we have it recorded. Okay, so first, leases. What are actually leases? And I came up with this standing on the shoulders of not giants, but leases. So what are leases? And that's a protocol mechanism we SMB has, and it's basically a mechanism for caching. So I better not. So I have to do that. What Volker laughs. Move my glasses here, and then switch, looking over you at all the glasses. So it's basically a caching mechanism. So it allows the SMB client to cache data and file handles on the server. And the idea is to improve performance, reduce round trips, because if the client has some stuff cached locally on the client side, it doesn't have to ask the servers, right? So it avoids round trips to the server. It reduces the load on the server, because the server doesn't have to process all these requests then, because it's all just done locally. So it's a performance improvement, and one nice thing I found is this image on the right about performance engineering, comparing A and B, some workloads, and you want to understand what is the performance different, how can we do it better, and analyzing whether A or B is more efficient takes. So performance engineering is really, really hard, but luckily with directory leases, this is really not the core problem, but this is something who is working on performance is probably familiar with. So a quick example of leases in example. I tried to come up with a nice picture describing this. So you have a client, you have a server, time flows from top to bottom. On the client, you have an application, and that application does some file I/O. It opens a file, and then later it reads and writes and does some stuff. And what it does initially, when it opens the file, it requests an RVH lease from the server, and that means read, write, and the handle. So it requests the right to cache, reads, writes, and opens and closes, and that's then what it does. So initially, there is an incoming read request from the application, and this is basically what happens here is the SMB client in some client, right? That takes the application requests and converts them into SMB requests. So the initial read, of course, has to be sent to the server because no data can be cached at that moment on the client. But then subsequently, having the RVH lease, if the client gets a request for a write, a read, it's just answered locally, right? It doesn't go to the server. And more interestingly, and these guys took me more time to wrap my head around in the last 10 or 15 years, being able to actually also cache closes and opens, right? So at that point, actually the application who has opened the file closes it and says, okay, I don't want to use it anymore. But what the SMB client does says, okay, I don't care. I don't send the close to the server. I just do that locally, tell the application, okay, file is closed. And what it allows is when the application later comes back and opens the file again, it's still cached. So it doesn't have to open it again, right? So there's no request there. And then possibly at some time later, as we have stuff cached on the client, sometimes you have to flush your buffers, right? And in this particular case here, I've tied it to the close, but that's not functionally related. Just happens here in my specific example, right? That at some point here, the client, the application does a close, and then the client, for some reason, says, okay, now I flush my buffer for whatever reasons, right? And this is the great benefit, that these four guys here don't get sent to the server, right? Next slide, okay. So, more details. So, as mentioned on the last slide, we have granular caching, right? You don't say, okay, I want to open this file and I want to cache everything. You can say, I want to cache read, writes, and handles. In some certain combinations, not all of them are allowed. And the very interesting bit is that with each request to get a lease, the client provides a lease key. And the cool thing is that allows having more than one open sharing this cache. So this kind of ties it together, right? So you can actually have two opens on the same file doing reads and writes, and the client can just have a shared cache on different handles on the client. Okay, so this is basically the top example here, right? So you have some file, and you have multiple opens on the client, and you have a lease key, which is a 128-bit number. Do we have that on this slide? Yes, it's there. So, but my lease key is just 1. And the lease cache state is RVH, right? So you can have two opens, and everything is just cached on the client. And if you have more leases then you will have a different lease key that happens to be on a different file B. And then, of course, you can also have, on the same file B, more leases with a different lease key. And those will not be compatible. Those will be concurrent. That is why these are, for example, these can only be RH leases. Those can only be shared for use for caching reads and handles, not for writing. Right? That can only be done if you have only basically a single lease attached to a file. And then being able to cache stuff on the client. Of course, you would want to have some kind of cache coherency, ideally, right? So what happens if one client has stuff cached and then comes another client who accesses the same data, what happens? Well, you have some kind of cache coherence protocol built into there, and that is called a break, lease breaks, where the server notifies the client to flush its cache if it has flushed writes. It tells, okay, I'm going to break your write lease now. If you have cached data on your client, then please push it back now to the server. Now is the time. Or if it's a read cache, if the client has cached data for reading, then it would just drop the cache and say, okay, I'm done with it. And one interesting bit that this causes as these breaking of read leases, where the server tells the client, so I have concurrent access to this file. So you must drop your cache data that you've read before. And this is done in an async fashion, and the server doesn't wait for a response from the client. So this can basically cause stale reads for the second client. So suppose you have a situation like this, where you have two clients connected to the server, and both have opened the same file. Time flows from top to bottom again. And in this case, there's no lease, no caching, right? So we don't have a problem. Client 1 writes to the file, and then it tells the other client via some communication side channel, I'm done with writing, you can now read the data. And I mean, what is our expectation now at that point in time? When that client gets that message and then wants to read that data, should it be there or not? Yes, yes. Anyone know? Any knows? Okay, so and in this case, that's what's going to happen, right? With the SMB protocol, as long as no caching is involved, that client will read the data that is written there. But if that client has a read lease and that client does a write, that sends a lease break to that client. Now, and for some reason, that maybe this is going over different communication channel, different link, whatever, than this communication side channel that I've put in here. For some reason, maybe this gets delayed. It just takes a little bit longer until it finally arrives at this client and says, okay, read lease break, discard your cache. So what happens if, at that point, the server does not wait to acknowledge the write. It immediately tells the client, yeah, I've broken the read lease. That guy even doesn't know about that at all, right? It's completely transparent for him. The server just says, okay, your write was successful, and then that client says, okay, cool, my write was successful, as in the previous case. It sends the message to that client, and the message arrives at that point in time. So before it receives the lease break message, it gets a read here from the application, and it reads stale data, right? So this can happen, and to me, this kind of was I knew about that for many years, but it never really became. I never really became fully aware of that. That we kind of have this problem with leases in SMB. And that was the question that was the thing I wanted to discuss with you, like what I asked 30 minutes ago. So the thing is, I think I removed that slide here. Typically applications that do these kind of things, right? Typically they don't do this. They use some kind of other synchronization primitives, like byte range locks. Like in Windows, not actually allowing this scenario, like this client opens the file and says nobody else is allowed to open this file. So using share modes and basically saying no one else is allowed to open the file in the first place. But if you do this, if you have an application that really just does that, then you can have a problem. But in real world, I guess apparently applications use different synchronization mechanisms and don't rely on this, luckily, right?
Okay, I probably should know this, but what happens if a client has a handle lease on a file, like whatever, read write, anyway, with a handle aspect?
That has to wait.
Yeah, no, following question. If now behind this handle lease, it's doing an open again that requests a different kind of lease on the file behind the handle lease, is that possible, or what happens then?
I don't fully get the question. You mean if you have one open with a handle lease, read handle lease or something, and then another open comes in?
No, the same client, because it is because of the age, it is allowed to do opens behind the lease. So what if that open again requests?
Open is fine. So you can have multiple opens on the same file sharing a read handle lease, for example.
Yeah, but if the same client requests an open with a different kind of lease behind the handle lease.
What do you mean by behind the handle? So if there's there are certain allowed combinations. So if the other client, for example, requests a RVH lease, then the right lease will not be granted. Because those are not compatible.
I meant a single client.
Sorry?
I meant just a single client. So client makes an open with a read-write handle lease, for example.
If it does use the same lease key, it will upgrade the lease.
Upgrade, okay.
Yes.
That's the answer. Thanks.
Yeah.
Yeah, I should have known about this. Thank you very much.
Okay, so moving on. So we have this great mechanism of leases for files, and in 2010, 2011, Microsoft said, hey, why not use something like this for directories, for allowing to cache directory metadata on clients. And it was introduced with SMB 3.0 in, I don't remember exactly, but in that time frame, 2011, 12. Initially presented at SDC, I think at 2010. So it's a while back. I mean, 12, yeah. The precise date doesn't really matter. It's some time back. And the idea was to move from a caching mechanism that was already there, right? So it's not that the protocol and then in the end clients were not able to cache directory contents on the client, but that mechanism was kind of a best effort mechanism. So there were no hard guarantees about the metadata consistency. That was basically based on change notify. Don't know if probably many of you will be aware of that term after attending so many presentations here at the conferences. And this allows, as this moves from a best effort to a cache with higher guarantees, it allows then the clients to cache those directories for a much larger period of time, right? So the previous metadata cache in Windows, for example, that was based on the change notify, it had some configurable timeouts and configurable number of files and directories that would be cached for some configurable amount of time and all that. And that was typically, as far as I remember, most of them were quite short-lived, right? So you open a large directory, you query the contents, and then you cache it on the client, and 5 seconds later, the client says, okay, I discard my cache because the caching time is over. I'm not sure it was 5 seconds, but I think it wasn't really very longer. You could change it in the configuration, but that still doesn't solve the basic problem, right? That you have your timeout-based cached. And by doing this and then allowing to really allow clients to cache that stuff for much longer time on the client, we get back that from the initial slide, round trip reduction, latency reduction, server scalability, so great thing. And so the better thing is we already have it in Samba. So Samba 4.22 released in March. Where's Metze? Samba 4, or who remembers Samba 4.22 released in March? Ships with a working implementation of SMB3 Directory Leases in Samba. So it's out like 6 weeks, 4 weeks, something like that. Still very new, baking, still warm. So it's behind an option. Of course, in Samba we have everything behind an option, but the thing is, this one is enabled by default, right? So when we discussed this, we thought that, okay, man, this should we be scared of this, and what do we do enabled this by default or no, but we jumped the ship and said, okay, come on, leases are working, and we worked so hard on it, and we wrote so many tests, so it's surely working, and we enable it by default. On a standalone Samba server. On clustered Samba, and Günther reminded me of that yesterday, on Samba with CDDB, so on clustered Samba, it's disabled by default. And there's no way to change that from the configuration. You have to do code changes currently. And why that is, I try to remember to point that out later on when I get to some internal stuff that I try to explain about lease break handling for directory, for leases in general. I will try to remember to explain why that is. And another thing I like to point out is that it basically assumes SMB-only access to your file system, like we do for leases, right? So if you have local access via other protocols or just directly local and you change files and so on, and then you already, with the SMB2 leases for files, you risk data corruption, right? Because Samba is not aware of that for leases if you have local file system modifications. And the same basically translates and applies to directory leases. So we have this kernel oplogs option, which is the Samba way of getting file system integration to be made aware of changes via other protocols. But that is disabled by default, right? So one thing you could do is basically enable kernel oplogs, and then things should work, even with access from other protocols. And one thing I'm occasionally spinning in my mind is how to improve here would be basically extending our notification process and subsystem to not only track explicit change notify requests, but to basically track file handle leases and then use this mechanism for breaking handle leases, more on that later, in order to allow then also access, to have working access with cross-protocol support. So what does such a thing look like? This is probably the boring stuff. I would say, I don't know, but anyway, some internal details. First, what does it do? But I think we've already got that covered. The client can cache handles, and in that case, not just for the files, like in the example initially, but for directories. And it allows caching then metadata on the directory, like file contents. What is there? What is inside the directory, in the file metadata of the directory, of items inside the directory? But not recursively, right? Just to point that out, just for the immediate contents of the directory. And then we have granular lease levels, like for files. And in the case of directory leases, only R and H are ever granted, so only an R lease that goes with being able to cache the directory metadata, and an H lease to protect the directory handle and actually be able to do caching for extended period of time anyway. Because without an H lease, if the client receives an application close, then the client would have to send the close to the server and basically drop the cache. If you don't have a handle anymore to attach the cache to, you basically have to throw away the cache. So that's why directory leases, what you will see is that clients will always request an RH lease in combination. And write leases are not granted. So you can't create files on the client and just cache that and say, I don't send the create to the server. The application is creating a file, but I just keep that locally cached. And maybe I will send the request to create the file onto the server later on. That's not happening because write leases are not granted. Right? So it's basically a read-only mechanism. And the protocol changes are, the on-the-wire protocol changes are quite small. So there's basically a new create context, lease v2, that has an additional lease key. some reserved bits that we can ignore. Lease epoch we can also ignore, that is used for a different feature, and some flag that gets used. And the way how that works is the directory lease key apparently basically ties together two lease keys, and that is the lease key of the object itself and the parent directory. So in these create context scenario, when the client sends a create request to the server, for example, to open a file, then it takes a lease key for the file itself and puts it here into the lease key. And then it takes another lease key for the parent directory and puts it there. And then it sets that flag inside there in the existing flags fields. And that lets the server, okay, this is a request working with a directory lease that was previously granted on a directory where the request was just to open the directory with that same parent directory lease key put in there, just when opening the directory. So that's what I got the order wrong, right? So that's what happens first. Open the directory with a lease key for the directory, and then a subsequent open for an open in that directory puts that parent directory lease key there in the parent lease key field. So it's a little bit mind-bending looking at you. Can you follow? And then what that builds basically is kind of this hierarchy, right? So assuming like this /dir, this would be the root directory of the shared SMB3, right? So that's the share root. So you have this lease key for the object itself, and in that case, as that doesn't have a parent, the parent lease key is 0, right? And but then it triples down. So the lease key 1 from that directory gets used as parent directory lease key in this these combinations here when working on subdirectory in combination, right? So the new lease key for the object itself and the parent lease key, and so on. So that's what ties it together. And then, as with leases, so if you allow caching, you have to do some cache coherence stuff, and so you have directory lease breaks. And the mechanism is basically this. Next slide. I mean, I doubt not explain this in detail because I'm probably too nervous to explain this algorithm. But I mean, basically, it's pretty straightforward, right? You just compare lease keys. Do they match when I get an open? Is it the right parent lease key? If it's not the correct parent lease key, if there's or no parent lease key is provided at all, then we do a break and so on, right? So the implementation of the core lease break algorithm is pretty straightforward. So the more interesting bit then is what actually would trigger lease breaks from the file system perspective, right? What kind of changes? And of course, I mean, you would expect anything to break the read lease that allows caching of the directory contents on the client for anything that changes the directory, like creation of new files or directories or rename of children in that directory, deletion, modification of timestamps or DOS attributes, dare to say. And all that, like for file leases, is done asynchronously. So it's basically a loose metadata cache for some bounded time, as long as it takes for the read lease breaks to travel to the clients. And they get that lease break notification and drop their caches. Right? So you have some time window where someone else does a modification, the read lease break gets sent, and if in between on that other client that metadata from the directory is accessed, you return stale data. Right? But for directories, who cares? If you have like a few milliseconds where you get not 100% precise view of the directory. So that's for the breaking of the cache invalidation of the cached directory metadata. And then we have breaking of the handle lease. And their semantics are basically the same as for files. So if you have access that is conflicting with existing opens, so suppose you have like someone else wants to open the directory for deletion, or there are renames on parent directories, and Windows is picky about that, and this is what basically then also breaks the handle lease on the client, which is the core mechanism for the client to hang its cache on. So implementing directory leases in Samba, how hard can it be? So I picked the work up, and I thought, okay, the first thing to do is probably write tests. So initially I had only implemented a few tests, so I did more tests, and I compared against Windows servers. So run this test against Windows servers to really nail the behavior down and understand the behavior, and fill in a few gaps that I knew that were there in handling of all the required metadata changes to make sure to catch all points in the Samba server where we get changes from other clients, and to make sure to trigger a directory release breaks then there for all cases. But at some point I realized, oh wait, so as mentioned before, directory releases stands on the shoulders of leases. And oh crap. We had an open bug. Unfortunately, I don't have the bug number here. That we had a deficiency in our 8 handle lease handling on files. And one of them was basically setting delete on close. So that's the way for Windows as the SMB protocol to delete a file. So you open the file, either directly with the open, you set a specific flag, or you can also set that flag later, as is shown here with a SMB2 set info request to set the delete on close flag. And then when the client closes that file, then it gets deleted. And the thing is, there is a difference in behavior if you have other opens on the same file. So suppose you have this guy here on the left, client A, that opens the file, and these two guys are now working on the same file. So this one just opens it with a, suppose that should say RH lease, so with a handle lease. And the client closes the file, but as it has an H lease, it doesn't get sent to the server. So from the server perspective, this file is still open with an H lease, right? And so now this other guy comes in, and it says, okay, I want to open that file, and I want to delete set on close, because I want to delete that file. And that should happen when I finally send the close to the server. But what happens is, at that point, you have to check if there are other opens on the file. And if there are, you are not supposed to delete the file. That happens when the last handle on the file is closed. So at that point, the file is not closed. And it says OK here. Yes, it says OK. And then we continue here, sorry. Just nothing happens. The close happens, but the file is still there, meanwhile here. And then at some point later, that client here finally sends this deferred close, which is the last handle on the file. So at that point, the file gets deleted. And what is supposed to happen is this. That's basically the same scenario. Client on the left has the file open with an RH lease. It closes it. It caches the close. It doesn't send it to the server. So from a server's perspective, it's still open. This guy comes in, opens it, sets delete on close. And this was the missing piece. You have to send a handle lease break to the other guy. And this request to set the delete on close, it waits on the server. It's processed asynchronously. The client just gets back a anti-status pending, I think it is, right? And then when that client acknowledges the handle lease break by saying, okay, yeah, I was just caching it. Here's the close, right? Then we close the last handle on the file on the server. 10 minutes left. Oh my God. And then the set delete and close get acknowledged to the client. Then comes the close, and then the file is deleted, right? So you have a different behavior here, right? So that's why it's important to try to break handle leases for scenarios where setting the delete on close, and that was not happening, and that had to be implemented, and that turned out to be quite complex. So we had to add some kind of generic infrastructure here, and so this is a function that is the front end to this complex infrastructure that works asynchronously. So in best Samba manner, it is a send function. It also has a receive function, and that does all the magic for triggering this HD break. There's a question.
That's optional behavior, right? That's not required by the protocol. The handle
What
break.
Windows does.
Windows does it?
Yes.
Is that mentioned in the document?
That's a good question. I would say I think so, but
It makes sense to do it, but it seems somehow optional.
Yeah, and it becomes worse.
Oh, okay.
It becomes because you
All
have
right,
to
I'll
do
stand by.
that same dance also in other places where it's even more
Okay, I
inconvenient
guess my only
for the
point is
server.
you may have discovered something missing from the document that we should report.
Yeah, I don't remember, so I'm not good in thinking while giving the presentation here. I'm in talking mode, so yeah, so keep going. Yeah, and I guess I have to speed up. So there was setting delete on close, and we basically, okay. One other question.
Tom, that it is there in the documentation.
It is there.
It is there in the
It is there.
documentation.
Yeah. So a must or what?
I think it's a behavior.
It's behavior. Yeah.
Nonetheless, it's not required. So I want to hear why.
But for somebody that has always proven to be good to implement Windows behavior, right? So basically, the same thing happens, has to be done for initial delete and close. So what we had here, the scenario before was using a set delete and close. So that is an explicit SMB request and set info request that sets this delete and close. The other variation to delete a file is using initial delete and close, and that flag is then basically already sent to the server when it does the open. So with the SMB2 create, it sets the flag, initial delete and close. And that means the client doesn't have to send this explicit set info, it just sends a close and then the file gets deleted. And there's a difference in at what time you have to break the handle lease when processing this initial delete and close stuff, right? Because basically you have to do the deletion of the file, and before you do the deletion, check are there other opens with a handle lease, and then try to break them. You have to do that when you do the close, and you have to do a close of a file internally, and when you get a tree disconnect from a client, when you get a session log off, and even when you get a TCP disconnect from a client. You have to walk your list of open files, see are there any open files with this initial delete and close set, and then postpone processing of all that stuff, do it asynchronously, and first break the handle leases of all that stuff. And when that comes back, in the end, then you can delete the file. Do I have a slide of here? No, that's rename, okay. If there are no other opens, if there were cached opens by the clients, right? And that's Windows behavior. I tested that what Windows does.
Sure.
Right. No.
Okay.
So more problems with rename. The same, not doing handle lease breaks. So Windows behavior if you rename a directory. So which one is doing what? That one is doing the rename, so this one is just doing an open. Okay, so this opens a file inside a directory. So it says, okay, you have it open. The application says, close that file, I don't need it anymore, but it has an H lease, so the close is cached. It's not sent to the server. The handle is cached on the client. So meanwhile, over there, that client comes in and says, I want to rename the parent directory of the file that guy had opened here. So it opens here, and then it sends a rename request to open the directory from the current name to something else. And then at that point, the Windows specifies that you have to check if there are recursively open file handles inside that directory. And if there are, you have to say, access denied. Can't do that. Sorry, go away. So, but the thing is, that guy has actually closed the file. It's just a cache open. So the same applies here. Do I have a slide for that? Yeah. You have to try to break the handle lease and see maybe the handle was just cached. Client sends the close request, so basically the deferred close from open here. Meanwhile, the request goes async, has to wait, and then if a close comes in, then we check, okay, was that the last handle? Okay, no more handles open in the directory now, so now we can rename at that point, rename the directory. I mean previously, it's an obvious behavior preference, right? Previously, it was just, now, go away. So, another one. Not checking if the destination file of a rename has an open handle lease. And actually not checking at all. So we are really bad. So if we got a request for a rename here from source to destination, is that the scenario? Yeah, I have it covered here. Okay, so that guy has the destination file open, right? And that guy,
Without a lease.
in that case, apparently without a lease.
On the left, he's
Yeah.
without a lease.
This is not about this. This is about a data corruption bug, basically, in Samba. Because we get the rename request, and we don't check at all on the destination if the destination was opened by any other client. We just said, OK, boop, rename. Yeah, OK, so don't have any slide for that. So you basically have to do the same, right? Before you have to check. And if there's a handle lease, you have to check, OK, maybe it was a deferred close. Tell the client, send the lease break. Maybe it sends a close, and then you can proceed. Otherwise, you can't. And then the rename would fail because there's an open file on the destination. And you must not allow that. You should fail with anti-status access denied in that place. And not just send, so with an OK here. OK, so I made some progress. Guess there's not that much to cover. So one thing that I thought that would be really, really easy to drill into and come up with some nice numbers to share here in my presentation. My idea was, OK, I shared some low-level technical details. So what is the real-world benefit in the end of all that shit, right? So and so I tried to come with some workloads with a Windows client, and then with Samba, with directory leases, some workload where I could count packets with GCP dump, see how many requests go over the wire for certain scenarios. And I couldn't really find any real-world workload like browsing Explorer, going through directory hierarchies, opening a file. What else did I try? I think I actually installed LibreOffice to have like a directory tree where there's a file and I open it. So, and of course, making sure every time I accessed that stuff before, so make sure it would be cached on the client. And then do the experiment, go there again, do something, is it cached? Do I see a number of packet reduction or not? And the thing is, I wasn't really able to provide any nice numbers here. Only one thing was nice. And that is probably one of the most important applications in the world. That is Command Exe, command prompt on Windows, doing a recursive, that's /s in Windows, a recursive directory listing of a large directory tree, right? That finally showed it. That without directory leases, we have 703 packets, and with directory leases, only 71. I don't know the exact reasons. I guess what I saw on the wire is that the client still requests change notification requests for the directory, and I guess that's an application thing. So I assume that it's just Windows Explorer itself that requests these things, probably. So there's room for improvement in Windows Explorer, it seems, because it really does a lot of opens of the directory, change notify, and then, no, he says, OK, Tom not, no.
guessing here.
Uh,
It would be very unfriendly for Explorer to hold leases. It would be.
it does?
It would interfere with everything. It would just be a mess.
So it does request. So it does definitely it does request directory leases. Yeah, yeah, definitely.
Surprised. Well,
It
you
just
said
does
that it's
both.
not taking full advantage.
Yes, yeah. That's just what I see on the wire.
It's probably trying to, you know,
Be
if
yeah,
somebody's just
and
browsing, you know.
so it requests directory releases. So and I actually also tested that against the Windows 2025 server to make sure. Oh, maybe I screwed up something in my Samba implementation, or there's somewhere a behavior difference that triggers that behavior in the Windows client. But no,
Well, in that
same
case,
behavior
what do
against
you mean by
Windows
not taking
2025.
full advantage? I mean, are you just guessing?
So what, for example, this scenario, so you have a directory tree, A, B, C, and then a file inside there. And then you go through that directory tree once, open that file, close that file, and then you do it all again. And then I was kind of expecting, okay, maybe so I saw the client doing directory release requests on those directories, but it does just a lot of other stuff. So in the end, when I just did a TCP dump quickly on the server and compared the numbers, I didn't drill into all the network traces to really understand what is going on exactly. I just checked the numbers. And for workloads like that, I just saw no difference in the number of packets. Right? So
You opened Explorer, you drilled down to directory C, then you double-clicked the file. Then you closed Explorer and reopened it?
and reopen it, exactly. Yeah. So go back to the directory tree, click down through the directory, and then and I only count the number of packets, of course, the second time I traverse the directory tree, right? And I get basically the same number of packets with and without directories, even against Windows 25.
If you don't
So
close Explorer, and you just simply go back up the tree and come back down, does the same?
I haven't checked on that level. Yeah, if it's depending, I don't think it's really depending on having the windows open. So as far as I remember, yeah, it should. But yeah, so gonna have to. Oh, time over. So what I did, it allows caching for the client. So surely the client will make some use of it. And in theory, it has benefits. And in practice, the only thing that I could find were some numbers from Microsoft. From 2011, from Storage Developer Conference, and a presentation from Molly Brown and Matthew George, who ran FSCT benchmarks. And they said, it's good. Yeah, it does its job, right? So, sorry, I just can only share this data here from 2011, and it's a great thing. It does its job. Okay, time over. That's basically it. So.